Why did a team of federally funded ecologists in northern Wisconsin spend 3 years and millions of dollars deliberately killing a perfectly healthy lake? What does the silver content of a Roman coin minted in 270 AD have in common with a glacier in West Antarctica that a NASA scientist declared unsavable in 2014? And why did a Danish physicist at Brookhaven National Laboratory die at 53, convinced he had found the equation behind every catastrophe in history, while the rest of the scientific community looked the other way? Those three things are the same story. They are connected by a single mathematical finding that has been published, verified, and replicated across 4 separate scientific fields over the past 4 decades. And that finding says something about the system you are sitting inside of right now that is genuinely difficult to say out loud, because it is not a warning. Warnings are about the future. This one is about the past. A specific, calculated threshold, the moment a system becomes too complex to recover, has been identified. And for several of the systems that your life depends on, the crossing already happened, quietly, in the data, before anyone held a press conference. Tonight we are going to follow the math from a sandpile simulation in 1987, through a dead lake in Wisconsin, to a NASA telephone briefing on May 12, 2014, to the silver coins of a dying empire, to a planetary dashboard showing 7 of 9 warning lights in the red. Settle in, get comfortable, and if you are not subscribed, now is the time, because by the end of this one, you are going to understand exactly where on the curve we are standing, and why the scientists who built the instrument to measure it have gone very, very quiet. If you want more like this across physics, collapse, deep history, and the math behind all of it, the Patreon is where those longer conversations happen. Let's start where it started. In 2008, a team of ecologists in northern Wisconsin did something that no research team had ever attempted before. They decided to kill a lake. Not by accident, not through negligence. They did it on purpose, methodically, over 3 years, with millions of dollars in federal funding and the full institutional backing of the University of Wisconsin and the National Science Foundation. The lake was called Peter Lake. It was small, about 18 acres, tucked into the Vilas County forest near the town of Boulder Junction. It had a healthy population of minnows, stable algae levels, clear water, a perfectly ordinary freshwater ecosystem, minding its own business in the middle of nowhere. And Stephen Carpenter, the limnologist who ran the project, looked at that lake and decided to push it over a cliff, slowly, while measuring every single thing that happened on the way down. The method was almost comically simple. Every year, starting in 2008, Carpenter's team added largemouth bass to Peter Lake. Not many, at first, just enough to start tipping the food web. The bass ate the minnows. The minnows had been eating the water fleas, so now the water fleas ate the phytoplankton. And gradually, over months and then years, the lake's entire biological community began to reorganize itself from the inside out. Carpenter had an adjacent lake, called Paul Lake, sitting right next door, untouched, monitored with the same equipment at the same frequency, serving as a control. Everything that happened in Peter Lake could be compared day by day, data point by data point, against a system that was not being pushed toward death. But killing the lake was not the point. The point was to watch it die, specifically to see if the mathematics of dying had a signature, a warning signal, something that showed up in the data before the collapse actually happened. Because if it did, if a dying system emits a detectable mathematical signal before the death is visible, then that same signal might be detectable in other systems, larger systems, Systems that nobody was deliberately pushing off a cliff, but that might be falling off one anyway. And here is what Carpenter found, published in Science in 2011, volume 332, page 1079. 12 authors, 3 years of continuous monitoring, millions of individual measurements of water chemistry, phytoplankton concentration, zooplankton abundance, dissolved gases, bacterial populations, and physical water properties. And the result was this. The warning signal was real. It appeared in the manipulated lake more than a year before the ecosystem actually collapsed. It did not appear in the control lake. The statistical fingerprint, a specific pattern of rising variance and increasing autocorrelation in the lake's chlorophyll data, showed up like a heartbeat slowing down on a monitor. The mathematics screamed that the system was losing resilience, that it was approaching a threshold it would not come back from, that the regime shift was not a possibility but an inevitability. And the signal was clear, unmistakable, and visible to anyone who knew what to look for. The phytoplankton got hammered. Carpenter's own words. The system became one where the phytoplankton fluctuated wildly, driven by the cascading effects of the bass introduction. And at some point, the system snapped into a new mode. That snap was the regime shift. The Clearwater Lake became a turbid, algae-choked lake, and the signal that predicted this snap had been flashing for over 12 months before it happened. I want you to hold that in your mind for a moment. A team of scientists built an instrument that detects the mathematical signature of a system approaching a point of no return. They tested it on a real, living ecosystem. It works. It detected the death of that ecosystem more than 12 months before the death actually happened. And here is the part of the story that changes everything. That instrument now exists. It has been refined, validated, replicated across dozens of studies in ecology, climate science, neuroscience, and economics. And in the years since Carpenter's experiment, that instrument has been pointed at the Amazon rainforest, at the Atlantic Ocean's circulation system, at the West Antarctic ice sheet, at coral reef ecosystems worldwide, at the global climate system as a whole. And every single one of them is flashing the same signal. That is not speculation. That is published, peer-reviewed science, sitting in the pages of Nature, Science, and the proceedings of the National Academy of Sciences. Papers with specific authors, specific institutions, specific dates, and specific numbers. And the part that should disturb you is not that the signal exists. It is that several of these systems have already crossed the threshold that the signal warns about. The point of no return is not approaching. For multiple major Earth systems, it has already passed. The mathematics confirmed it. The papers were published, and somehow, the thing that should have been the biggest story in the history of human civilization was treated as a routine academic finding. This is the story of the calculation that proved a system can become too complex to save. What the math actually says. Who did the math? What happened when they published it? And why the answer to the question in the title of this video is not a warning about the future. It is a statement about the past. I want to stay with Carpenter's experiment for another moment because the details matter. The detail is the credibility. Peter Lake sits in the University of Notre Dame Environmental Research Center, a cluster of lakes and forest in northern Wisconsin that has been used for ecological experiments since the 1950s. It is remote. You reach it by unpaved roads through second-growth forest. The nearest town, Boulder Junction, has a population of under 1,000. This is not a metaphorical wilderness. It is actual wilderness, and the lakes in it have been monitored with an intensity that makes them some of the most data-rich aquatic ecosystems on the planet. Carpenter's team did not just dump bass into Peter Lake and check back in 3 years. They monitored the lake continuously. Daily measurements of dissolved oxygen, pH, water temperature at multiple depths, chlorophyll concentrations, phytoplankton community composition, zooplankton abundance by species, fish population surveys using electrofishing and mark recapture methods, dissolved organic carbon, total phosphorus, and carbon dioxide flux between the lake surface and the atmosphere. They had automated sensors taking readings around the clock. They had research boats on the water multiple times per week. The adjacent control lake, Paul Lake, received the same monitoring at the same frequency with the same instruments. The data set that resulted from this 3-year experiment is one of the most comprehensive ecological time series ever assembled for a single body of water. And throughout all of that monitoring, during the first 2 years, the lake looked fine. If you visited Peter Lake in 2009, a year after the bass introduction began, you would have seen clear water, healthy vegetation, fish swimming. The minnow population was declining, yes, but the lake was still recognizably the same lake. The water clarity was still acceptable. The phytoplankton levels were within normal range. An observer without the statistical training to read the time series would have concluded that the lake was coping with the disturbance. But Carpenter had the time series, and the time series was telling a different story. The autocorrelation in the chlorophyll data was climbing. The variance was increasing. The recovery time from small perturbations, the time it took the phytoplankton community to settle back to its baseline after a wind event or a temperature swing, was lengthening. The numbers were not dramatic. They were not flashing red on a dashboard. They were subtle, detectable only through statistical analysis of the daily measurements. Invisible to the naked eye, the lake was losing resilience, and the only evidence was in the math. Carpenter later told reporters at the University of Wisconsin, and I think his exact phrasing captures something important about the nature of this kind of knowledge. He said, "These regime shifts tend to be hard to reverse. Not impossible. Hard." And the word hard in the context of ecosystem ecology means that reversing a regime shift often requires reducing the stressor not just to the level that caused the shift, but far below it, sometimes to levels that are economically or practically impossible to achieve. The path forward and the path back are not the same. You cannot just undo what you did. The system has reorganized. Its internal feedbacks have changed. It is a different lake now, operating on different rules, and it will not become the old lake again without an intervention that is orders of magnitude more costly than the prevention would have been. Alan Tessier, the program director at the National Science Foundation's Division of Environmental Biology, who oversaw the funding, said this research shows that with careful monitoring, we can foresee shifts in the structure of ecosystems despite their complexity. The results point the way for ecosystem management to become a predictive science. That statement, said in 2011, sounds hopeful. It sounds like progress. It sounds like the instrument could save us. But 13 years later, in 2024, I read that statement and hear something completely different. Because predicting is not the same as preventing. And knowing that a system is approaching collapse does not mean you can stop the collapse. It means you can watch it happen with more precision. And in several cases, as you are about to see, the watching began after the collapse had already started. But to understand why that statement is so much worse than it sounds, you need to see where this mathematics came from. Because the instrument Carpenter used did not appear out of thin air. It is built on a foundation laid by 3 separate lines of scientific inquiry, developed independently in 3 different fields over the course of 4 decades. And the fact that all three converge on the same conclusion is, to me, the most alarming finding in modern science. Not because any one of them is wrong, but because when 3 different branches of knowledge, using 3 different methods, studying 3 different types of systems, all arrive at the same mathematical result, the probability that the result is an artifact drops to near 0. The first line starts with a pile of sand. It was 1987. Per Bak was 38 years old, a Danish theoretical physicist working at Brookhaven National Laboratory in Upton, New York. Brookhaven is a sprawling federal research complex on Long Island, about 60 miles east of Manhattan, run by the United States Department of Energy. It is the kind of place where serious physicists do serious work on serious problems, which is what makes it so strange that Bak was spending his time thinking about sand. Bak was born on December 8, 1948, in Brønderslev, a small town in the north of Denmark, the kind of place you leave if you are talented and ambitious, which he was. He got his doctorate from the Technical University of Denmark in 1974 and immediately moved to Brookhaven, where he was supposed to be working on phase transitions in condensed matter systems. The physics of materials changing state, insulators becoming conductors, water becoming ice, clean, respectable, well-funded work, the kind of physics that produces papers in solid journals and keeps your career on a predictable trajectory. But Bak had a personality that did not fit predictable trajectories. People who knew him described him as combative, brilliant, impatient, and convinced that most of his colleagues were asking the wrong questions. He was not interested in systems that behaved themselves. He was not interested in equilibrium. He was interested in the ones that did not behave. The ones that sat there looking stable and then, without any identifiable trigger, catastrophically failed. Earthquakes, stock market crashes, blackouts cascading across electrical grids, forest fires that started as sparks and became infernos. The pattern was everywhere in nature and nowhere in physics. There was no general theory. Nobody could explain why a system could absorb stress after stress after stress, and then, with one more addition that was no different from any of the previous ones, come apart completely. The question Bak asked was deceptively simple. What is the typical size of an avalanche on a sand pile? If you drop grains of sand one at a time onto a pile, and the pile occasionally avalanches, is there a normal avalanche? A most common one? An average? Something predictable? The experiment he designed with Chao Tang and Kurt Wiesenfeld, 2 postdoctoral researchers in the solid-state theory group at Brookhaven, was not conducted with actual sand. It was a computer simulation. They wrote a program that dropped virtual grains onto a virtual pile, one at a time, and tracked every avalanche that resulted. Each grain could cause a small cascading rearrangement, a large one, or no rearrangement at all. They ran the simulation for millions of grains, millions of avalanches, an enormous dataset, and then they looked at the distribution. What they found has not stopped being relevant for a single day since it was published. The avalanches followed a power law distribution. For every avalanche of size 10, there were roughly 10 avalanches of size 1. For every avalanche of size 100, roughly 10 of size 10. The relationship was precise, mathematical, and scale-free. There was no typical avalanche. There was no normal size. Small ones happened often. Enormous ones happened rarely. But the probability of any given size was governed by the same equation at every scale. The math that described a 10-grain avalanche was identical to the math that described a 10,000-grain avalanche. They were the same phenomenon at different magnitudes. And here is the finding that changed everything. Nobody tuned the system to produce this behavior. Nobody adjusted parameters. Nobody designed the pile to be in a critical state. The pile organized itself into that state naturally, inevitably, as a direct consequence of the process of growing. Bak called it self-organized criticality. He published it in Physical Review Letters on July 27, 1987, volume 59, page 381. The paper was 4 pages long. It was titled Self-Organized Criticality, an explanation of 1/F noise. It would eventually become one of the most cited physics papers of the 20th century, with applications in more than 24 fields. I want to make sure the implication of this lands with its full weight, because it is easy to hear sandpile and think toy model. This is not a toy model. What Bak, Tang, and Wiesenfeld demonstrated is that there exists a class of complex systems that grow through the accumulation of components and interactions that naturally and inevitably evolve toward a state where catastrophic failure events are statistically guaranteed. The system does not need an external shock. It does not need someone to make a mistake. It does not need a trigger. The catastrophe is not caused by something going wrong. The catastrophe is a mathematical property of the system itself. The sandpile does not need a reason to avalanche. It avalanches because that is what sandpiles do once they reach criticality. And the single grain that triggers any given avalanche is not special. It is not the cause. It is simply the last grain the system could absorb before the built-up instability expressed itself. For scale, think of it this way. Imagine you are stacking blocks. Each block makes the tower taller, more impressive, more capable of whatever towers are supposed to do. And for a long time, each block seems fine. The tower holds, it accommodates, it adjusts. And you start to think the tower is stable because it has always been stable. You start to think that stability is a property of the tower. It is not. Stability is a temporary condition of a system that is accumulating instability with every addition. The tower will fall. Not because of the last block, because of every block. Bak spent the next 15 years pushing this idea into every field that would listen, and many that would not. Earthquakes follow power law distributions. So do forest fires. So do extinction events in the fossil record. So do fluctuations in financial markets. So do blackouts in electrical grids. So do wars. Wherever Bak looked, he found the same mathematical fingerprint. Scale-free distributions, power laws, self-organized criticality. He wrote a book in 1996 called How Nature Works, published by Copernicus, in which he argued that self-organized criticality was the fundamental organizing principle behind most of the complex phenomena in the natural world. The claim was enormous, and the physics establishment responded the way it usually responds to enormous claims from people who cross disciplinary boundaries without asking permission. They pushed back hard. The criticisms were varied. Some argued that Bak was overgeneralizing from a specific model. Some argued that real-world systems do not perfectly match the idealized sandpile. Some argued that power law distributions can arise from mechanisms other than self-organized criticality. All of these criticisms have merit. Not every power law distribution means the system is self-organized critical. Not every complex system is a sandpile. The concept has edges, limitations, boundary conditions. And Bak, by temperament and conviction, was not great at acknowledging those edges. He saw the pattern everywhere and wanted everyone else to see it too. And his impatience with skeptics sometimes undermined his own case. But the core finding was never refuted. The sandpile model is mathematically rigorous. The power law distribution it produces is real, and the principle that complex systems can naturally organize into critical states where large-scale catastrophic events are inevitable, has been validated across too many domains to dismiss. Dietmar Plenz, the neuroscientist at the National Institute of Mental Health, recalled that in the 1990s, it was impossible to win a grant in neuroscience to work on self-organized criticality. There was no experimental evidence in the brain. The concept was theoretical. But since 2003, the evidence that the brain operates near a critical point has grown from scattered hints to a substantial body of work spanning EEG recordings, neural imaging, and cortical tissue studies. The brain, it turns out, organizes itself near criticality, as does the climate, as do ecosystems, as do financial networks. The pattern Bak identified is not a metaphor. It is a measurable feature of how complex systems work. Per Bak died on October 16, 2002, in Copenhagen. He was 53 years old. He had spent his final years at the Niels Bohr Institute and Imperial College London, still pushing, still arguing, still convinced that the scientific community was underestimating the scope of his discovery. And the question he left behind was the one that keeps me up at night. If self-organized criticality is real, if complex systems naturally evolve towards states where catastrophic failure is statistically inevitable, then the question is no longer whether any particular complex system will collapse. The question is whether you can see it coming, whether the mathematics of collapse has a warning sign, a signal that appears before the event itself, an early warning that gives you time. That question sat in the literature for 7 years after Bak's death, waiting for someone to answer it. In 2009, someone did. I want to tell you something about the way Bak's idea was received, because the institutional response to self-organized criticality mirrors almost perfectly the institutional response to every other finding I am going to describe in this script. And the pattern of that response is itself a data point. When the 1987 paper was published, the initial reaction was interest. Physical Review Letters is one of the most prestigious journals in physics. The paper was well written, mathematically rigorous, and offered an elegant explanation for a phenomenon that was genuinely puzzling. The citations started accumulating immediately. Within a few years, hundreds of researchers across multiple fields were exploring applications of self-organized criticality to their own systems. Earthquake seismology, solar flare statistics, evolutionary biology, financial markets, traffic flow, neural networks. The concept spread faster than almost any idea in modern physics. And then the pushback started. Not against the math, which was sound, against the scope, against the ambition, against the claim that a single organizing principle could explain phenomena across so many different fields. The physics community has a deep and understandable suspicion of universal theories. The history of science is littered with elegant ideas that turned out to be less universal than their creators believed. And Bak, by personality and conviction, was the worst possible advocate for a nuanced version of his own idea. He did not do nuance. He did not acknowledge boundary conditions gracefully. He did not say, this applies in these specific cases, under these specific conditions. He said, this is how nature works, and dared people to prove him wrong. The result was a polarization. On one side, a growing community of researchers finding genuine applications of self-organized criticality in their fields, producing real, validated, reproducible results. On the other side, a mainstream physics establishment that treated the concept as overreaching, borderline unfalsifiable, and uncomfortably close to the kind of theory of everything thinking that serious physicists are trained to distrust. And between the two sides, a gap where the valid core of the idea that complex systems can naturally organize into critical states where catastrophic failure is inevitable, sat unintegrated into mainstream scientific thinking, published but not absorbed, cited but not applied, available but not used by the people who most needed it. I keep noticing this pattern. Publish, cite, ignore. The paper is real, the math is sound, the citations accumulate, and yet the implication is never absorbed by the institutions that make decisions. The knowledge exists in the literature and nowhere else. It does not cross the boundary between what scientists know and what policymakers act on. It does not appear in the reports that reach desks. It does not inform the frameworks that shape responses. It lives in journal articles that are read by other scientists who write their own journal articles that are read by other scientists. And the cycle continues. And the sand keeps piling up. Bak noticed this too. Toward the end of his life, in How Nature Works, he wrote passages of barely contained frustration about the resistance to interdisciplinary thinking in modern science. He believed, genuinely, that the compartmentalization of knowledge into separate fields was itself a form of institutional failure. That the pattern connecting earthquakes and stock crashes and forest fires and extinction events was invisible not because it was subtle, but because the people who studied earthquakes did not read the people who studied stock crashes, and vice versa. The knowledge was there, the synthesis was missing. And the synthesis was missing not because it was impossible, but because the institutional structure of science did not reward it. He died before the synthesis happened. He died before Scheffer turned the theory into a diagnostic instrument. He died before Carpenter validated the instrument in Peter Lake. He died before Rignot used the word irreversible about an ice sheet. He died before anyone pointed the instrument at the Amazon and watched it flash red across 3/4 of a continent. He saw the sandpile clearly enough to describe its mathematics. He did not live to see the sand fall. Marten Scheffer is a Dutch ecologist at Wageningen University in the Netherlands. He was born in the Netherlands and has spent his entire career there, which is relevant because his scientific origin story is about as far from abstract theoretical physics as you can get. Scheffer did not start with equations. He started with lakes. Shallow, murky, nutrient-loaded Dutch lakes that smelled like rotting vegetation and attracted more municipal complaints than scientific interest. In the Netherlands, shallow lakes are everywhere. And in the second half of the 20th century, agricultural runoff loaded many of them with phosphorus and nitrogen, to the point where they flipped from clear-water ecosystems with rooted aquatic plants and diverse fish populations to turbid, algae-dominated systems choked with cyanobacteria. The flips were dramatic. One season the lake was clear, the next it was green soup. And the most frustrating thing for the water managers who had to deal with the public outcry was that reducing the nutrient inputs did not bring the lakes back. You could cut the phosphorus load by half and the lake would stay turbid. You could cut it by 75% and still nothing. The clear water state and the turbid state were both stable. Once the lake flipped, getting it to flip back required reducing nutrients to levels far below the point that originally triggered the transition. Scheffer spent years studying this phenomenon, and what he realized was that the flip was not random. The lake gave warnings. As it approached the tipping point, its behavior changed in measurable ways. The fluctuations in water clarity got larger. The time it took the lake to recover from small disturbances, like a temporary pulse of nutrients or a cold snap, got longer. The system became, in a mathematical sense, sluggish. It was losing its ability to bounce back from perturbation. Its resilience was declining. And Scheffer recognized that this sluggishness, this critical slowing down, was not specific to lakes. It was a generic mathematical property of any system approaching a bifurcation point, the kind of threshold where a small additional push causes a sudden, large, and often irreversible shift. The math behind this is not complicated in principle, although it gets complex in application. Near a tipping point, the dominant eigenvalue of the system's dynamics approaches zero. What that means in plain language is that the system's restoring force, the thing that pulls it back to its current state, after a disturbance, gets weaker and weaker. The system takes longer and longer to return to normal after being pushed, and the fluctuations around the equilibrium get larger because the system no longer damps them as effectively. These are measurable quantities. You can calculate the autocorrelation of a time series, which tells you how similar each data point is to the one before it. Near a tipping point, autocorrelation rises because the system is responding more slowly and each state increasingly resembles the previous one. You can calculate the variance, which rises because the system oscillates more widely. These are not metaphors. They are statistics, numbers, things you can put on a graph. In September 2009, Scheffer and 9 co-authors published a paper in Nature, volume 461, page 53. The title was Early Warning Signals for Critical Transitions. The paper reviewed evidence from ecology, climate science, finance, and medicine. It argued that systems approaching tipping points emit universal warning signals, rising variance, increasing autocorrelation, increased flickering between states, and these signals appear across systems so different in their physical details that they should not have anything in common. A lake approaching eutrophication, a financial market approaching a crash, a climate system approaching a regime shift, an epileptic brain approaching a seizure, a depressive patient approaching a psychotic episode. All of them, Scheffer and his co-authors argued, display the same mathematical signature as they approach their respective tipping points. The paper won Scheffer the Spinoza Prize, the highest scientific award in the Netherlands. He used the funding to establish SPARC-S, the Synergy Program for Analyzing Resilience and Critical Transitions, an interdisciplinary center at Wageningen dedicated to developing these warning signals across fields. He also co-founded the South American Institute for Resilience and Sustainability Studies and the Institute Paralimes at Nanyang Technological University in Singapore. In his spare time, he plays violin and guitar. He once combined his science and music into a performance called Concerted Science, which I mention only because the juxtaposition of a man who plays string instruments and detects the dying notes of planetary systems is the kind of detail that belongs in this story. But I want to come back to the instrument itself, because what Scheffer built and what Carpenter tested is something unprecedented in the history of science. It is a diagnostic tool for collapse, an EKG for complex systems, a way to look at a system, any system, measure specific mathematical properties of its behavior, and determine whether it is approaching a point from which it cannot return. Not with expert judgment, not with opinion, not with models that might be wrong, with statistics, with numbers derived directly from the system's own behavior. The system tells you it is dying if you know how to listen. And then Carpenter proved it works. I described the Peter Lake experiment at the top of this script, but I want to go back to it now with the mathematical framework in place, because the experiment takes on a different weight when you understand what it proved. Carpenter did not just show that a lake can be pushed past a tipping point. We knew that already. What he showed is that Scheffer's early warning signals, the specific statistical measurements that are supposed to appear before a critical transition, actually do appear in a real ecosystem under controlled conditions, with a control lake sitting right next to it for comparison. The warning signals were evident in the manipulated lake during reorganization of the food web more than a year before the food web transition was complete. That sentence is from the paper itself. The upshot, as Carpenter put it in the University of Wisconsin press materials, is a validated statistical early warning system for ecosystem collapse. The instrument works. And now the question becomes, what do you point it at? I am going to walk you through 5 things that the instrument has been pointed at, 5 systems, 5 readings, and by the end, you are going to understand why the title of this video uses the past tense. The first one involves a glaciologist on a telephone telling a room full of reporters something that nobody wanted to hear. May 12, 2014, a Monday. NASA's Jet Propulsion Laboratory in Pasadena, California, held a telephone press conference. The lead scientist was Eric Rignot. Born in France, educated at the University of Grenoble, Rignot is jointly appointed at the University of California, Irvine, and NASA's Jet Propulsion Laboratory. He has spent his career studying the ice sheets of Greenland and Antarctica, using satellite radar data. And by 2014, he had assembled the most comprehensive observational dataset ever collected on the glaciers of the Amundsen Sea sector of West Antarctica. 40 years of data, cryosat measurements, INSAR satellite interferometry, airborne ice-penetrating radar surveys from NASA's Operation Icebridge, an accumulation of evidence that no one could dismiss as preliminary or incomplete. What Rignot told the press conference that day is a sentence I need you to hear exactly as he said it. He said, "The system is in sort of a chain reaction that is unstoppable." He said, "A large sector of the West Antarctic ice sheet has gone into a state of irreversible retreat." And then he used the words that match the title of this video. It has passed the point of no return. Not approaching, not at risk of, not might. Past, past tense. Already happened. The paper was published in Geophysical Research Letters, Volume 41. Issue 10. The data showed that 6 glaciers in the Amundsen Sea sector, Pine Island, Thwaites, Haynes, Pope, Smith, and Kohler, were retreating faster than any previous measurement had captured. The grounding line, the boundary where the glacier sits on bedrock and holds back the weight of the ice behind it, had pulled back dramatically. In the Smith and Kohler Glacier, the retreat was 34 to 37 kilometers over the study period, and crucially, ice-penetrating radar showed that there was nothing underneath the ice to stop the retreat. No mountain range, no ridge, no natural barrier. The bedrock beneath these glaciers slopes downward as you move inland, which means the farther the grounding line retreats, the thicker the ice column it exposes to warm ocean water, which means the melting accelerates as it goes. It is a positive feedback loop with no natural break. Rignot likened it to uncorking a full bottle of wine lying on its side. The same day, a companion paper was published in Science, Volume 344, page 735. Ian Juffin, a glaciologist at the University of Washington, had been modeling the Thwaites Glacier specifically, the largest glacial system in the Amundsen sector. His simulations ran through multiple warming scenarios, from the most optimistic to the most extreme, and the conclusion was that under every scenario except possibly the very lowest melt rate, early stage collapse of Thwaites had already begun. The uncertainty was not about whether it was collapsing, but about how fast. His estimates ranged from 200 to 900 years before the collapse produced more than 1 millimeter per year of sea level rise. These 6 glaciers alone contain enough ice to raise global sea levels by 1.2 meters. That is 4 feet. To make that number tangible, 4 feet of sea level rise puts large portions of Miami, New York, Mumbai, Shanghai, and Lagos underwater during normal tides, not storms. It permanently submerges island nations. It moves the coastline of the United States inland by an average of several hundred feet, more in flat areas like the Gulf Coast. And Thwaites is not just a glacier, it is a keystone. Thwaites acts as a cork for the rest of the West Antarctic ice sheet, which holds enough ice for an additional 3 to 4 meters of sea level rise. So the irreversible retreat of the Amundsen sector is not just about those 6 glaciers. It is the first domino in a chain that could eventually produce 4 to 5 meters of total rise. Every coastal city, every port, every low-lying island nation, every piece of infrastructure built within 15 feet of the current waterline, all of it, not in the future, already committed. The commitment was made by physics sometime before Rignot measured it. He did not predict it. He documented it after it had already happened. I want to stay with Rignot's finding for another moment, because there is a detail that most coverage of this story missed. A detail about the bedrock. When Rignot and his team examined the ice-penetrating radar data from NASA's Operation Icebridge surveys, they were looking for something specific. They were looking for obstacles, mountains, ridges, any feature of the underlying bedrock that might slow or stop the retreating grounding line. Because in other parts of Antarctica, glaciers sit on bedrock that rises as you move inland. That geometry is stabilizing. Even if the coastal end starts to retreat, the grounding line eventually encounters shallower bedrock, which reduces the ice thickness exposed to warm water, which reduces the melt rate, which slows the retreat. The system has a natural break. The Amundsen sector has no break. The bedrock beneath these 6 glaciers does the opposite. It slopes downward as you move inland. The deeper you go, the lower the bedrock sits, which means the farther the grounding line retreats, the thicker the column of ice it encounters, which means more ice is exposed to warm water, which means more melting, which means faster retreat, which means the grounding line moves farther inland to even lower bedrock. It is a self-reinforcing cycle, a positive feedback loop in the purest sense of the term. Each step in the process amplifies the next step, and there is no topographic feature anywhere along the retreat path that could stop it. Rignot's team checked. They looked at every square kilometer of bedrock under the ice. There is nothing there. Rignot compared it to uncorking a wine bottle lying on its side. Once the cork comes out, the wine flows. You cannot recork it from downstream. The geometry of the system is such that the initial retreat, which has already occurred, guarantees the eventual loss of the entire sector, not because of anything that will happen in the future, because of the shape of the rock under the ice. The bedrock is not going to change. The mountains that would need to be there to stop the retreat do not exist and never did. The system was always vulnerable to this specific mode of failure. It just needed a push, and the warming of the circumpolar deep water provided that push, and now the feedback loop is running, and it will continue running until the ice is gone. The 6 glaciers contain 1.2 meters of sea level rise, but that is only the beginning, because Thwaites, the largest of the West Antarctic ice sheet, when Thwaites goes, the ice behind it is exposed, and the bedrock behind Thwaites slopes down even further. The total potential sea level rise from the entire waste is estimated at 3.3 meters. That is 10.8 feet, a number that is hard to make visceral until you start mapping it onto specific places. 10.8 feet of sea level rise puts roughly half of Bangladesh below the waterline. It submerges the Maldives entirely. It inundates large portions of the Netherlands, which currently protects 60% of its population with dikes and seawalls. Miami Beach ceases to exist. Manhattan below 14th Street floods regularly. The runway at JFK International Airport is underwater. The ports of Shanghai, Mumbai, Lagos, Jakarta, Bangkok, and Ho Chi Minh City are compromised. These are not projections. These are consequences of arithmetic. You take the coastline, you add 10.8 feet of water, and you see what is above it and what is not. And all of that was committed before Rignott held his press conference. The process was already underway. The feedback loop was already running. The bedrock was already the wrong shape. The only variable left was time. And Juffin's models gave us the time. 200 to 900 years, a range so wide it might seem meaningless. But the bottom end of that range, 200 years, is well within the planning horizon of infrastructure built today. A bridge designed to last 75 years, a subway system designed to operate for a century, a city built at a coastline that will not be a coastline when the bridge is still standing. This is the temporal gap in its most concrete form. The threshold was crossed in the past. The consequence will arrive in the future. And in the gap, in the years and decades and centuries between the two, everything looks normal. The ice is still there. The coastlines are still where they are. The cities are still standing. And the math, sitting quietly in the journal articles, says that all of it is already committed. The wine is already flowing out of the bottle. The lake is still clear. And the person who could read the chlorophyll data left the room years ago. I want to tell you about one more system before I bring this all together, because this one connects the Earth system findings directly to Tainter's framework in a way that makes the convergence impossible to ignore. In 2009, the same year Scheffer published his early warning signals paper, Johan Rockström at the Stockholm Resilience Center proposed the Planetary Boundaries framework. The idea was elegant and terrifying in equal measure. Rockström and his team identified 9 Earth system processes that, if pushed past certain thresholds, would destabilize the conditions that allowed human civilization to develop over the past 10,000 years. 9 processes, 9 boundaries, a safe operating space for humanity, defined not by politics or economics, but by the physics and chemistry and biology of the planet itself. The 9 boundaries are climate change, biosphere integrity, land system change, freshwater change, biogeochemical flows, meaning the nitrogen and phosphorus cycles, ocean acidification, atmospheric aerosol loading, stratospheric ozone depletion, and novel entities, meaning synthetic chemicals and plastics and other materials that did not exist in the biosphere before humans created them. In 2009, when the framework was first published, 3 of the 9 boundaries had been crossed: climate change, biosphere integrity, and biogeochemical flows. 3 out of 9, already past the safe zone, already operating in territory that the framework defined as high risk. In 2015, an update added land system change to the list, 4 of 9. In 2023, Catherine Richardson and 28 co-authors published a major reassessment in Science Advances, Volume 9. They used the latest data for every boundary and found that 6 of 9 had been crossed. Climate change, biosphere integrity, land system change, freshwater change, biogeochemical flows, and novel entities. And in September 2025, the Planetary Health Check report from the Planetary Boundaries Science Lab at the Potsdam Institute for Climate Impact Research added ocean acidification to the list. 7 of 9. 7 of 9 planetary boundaries. 7 of the 9 guardrails that define whether the planet remains in the state that allowed human civilization to exist have been breached. Johan Rockström, responding to the 2025 update, said, and this is his exact phrasing, more than 3/4 of the Earth's support systems are not in the safe zone. Humanity is pushing beyond the limits of a safe operating space, increasing the risk of destabilizing the planet. And now, I want to be careful about what this does and does not mean, because the planetary boundaries framework is sometimes presented in media as though crossing a boundary means instant catastrophe, and that is not what Rockstrom intended. The boundaries define a safe zone. Crossing a boundary means leaving the safe zone and entering a zone of increasing risk. The risk increases the farther past a boundary you go. Some boundaries have a hard threshold, a cliff, where crossing means irreversible change. Others have a gradient, where risk rises continuously but no single moment of crossing produces a catastrophe. The framework is a dashboard, not a detonator. But a dashboard showing 7 of 9 gauges in the red is not a dashboard you ignore. And the trajectory matters. In 2009, 3 boundaries were crossed. In 2015, 4. In 2023, 6. In 2025, 7. The number is not decreasing. It is not stabilizing. It is increasing at an accelerating rate. And of the 2 remaining boundaries that have not yet been crossed, atmospheric aerosol loading and stratospheric ozone depletion, ozone is the one that was actually improving due to the Montreal Protocol, which banned chlorofluorocarbons in 1987. It is the single success story in the entire framework. 1 boundary out of 9 where international cooperation actually worked and the boundary was respected. And even that success is being threatened by the discovery that some nations are illegally producing CFCs again, and by the unexpected ozone-depleting effects of certain industrial solvents that were not covered by the original treaty. The planetary boundaries framework, viewed through the lens of everything else I have described, is not just a status report. It is a measurement of the system's position on Tainter's curve. Each boundary represents a dimension of planetary complexity that civilization depends on. Each breach represents a subsystem that has been pushed past its threshold, and the response of the institutional system to the breaches, the Paris Agreement, the COP conferences, the Sustainable Development Goals, the Green Climate Fund, the proliferation of environmental monitoring agencies and regulatory bodies, and international working groups. Every single one of these responses is an addition of complexity, and every single one of them costs more than the previous one and returns less. The Paris Agreement, signed in 2015, has not prevented a single planetary boundary from being breached since its adoption. Not one. The boundaries that were in the red in 2015 are still in the red, and 2 more have joined them. The institutional response, the most complex international environmental agreement ever negotiated, has not reversed a single crossing. It has not prevented a single new one. It has added enormous institutional complexity, thousands of pages of rules and procedures and reporting requirements and compliance mechanisms and review processes, and the gauges are still moving in the wrong direction. That is not a criticism of the people who negotiated the Paris Agreement. It is an observation about where the civilization that negotiated it sits on Tainter's curve. The tool is not working, and the tool is the only tool available. And the response to the tool not working is to make the tool more complex. Sridhar Anandakrishnan, a glaciologist at Penn State University who was not involved in either study, called Ridnott's paper a really important piece of work about a critically important piece of the continent. The language was restrained, professional, the kind of thing scientists say when the findings are too significant to be dismissed and too alarming to be celebrated. The accelerating flow rates, the lack of pinning points, the sloping bedrock, all point to one conclusion, Ridnott said. The collapse of this sector of West Antarctica appears to be unstoppable. The fact that the retreat is happening simultaneously over a large sector suggests it was triggered by a common cause, such as an increase in the amount of ocean heat beneath the floating sections of the glaciers. At this point, the end of this sector appears to be inevitable. That finding, on its own, should have dominated the news cycle for months. It did not. It appeared, was covered for a day or two, and then receded behind whatever political story was running that week. And the reason it receded is the same reason that so much of what I am telling you tonight has never reached you. The timescale. Rignot is talking about centuries. The full collapse of the Amundsen sector will take hundreds of years. The sea level rise will arrive slowly over generations, and the human attention span, both individual and institutional, is calibrated to cycles of days, months, and election years. A catastrophe that unfolds over centuries does not register as a catastrophe. It registers as a fact about the distant future, something for grandchildren to worry about. But that framing misses the point entirely. The point is not when the consequences arrive. The point is when the threshold was crossed. The consequences are in the pipeline. They are committed. They cannot be stopped. The moment that matters, the moment the system became unsavable, happened in the past. Before Rignot's press conference, before his paper was published, before the satellites were even launched that eventually measured it, the ice sheet crossed its point of no return, and nobody noticed because the consequences had not arrived yet. That temporal gap between the crossing and the visible consequences is the defining horror of this entire field. And the ice is not the only system where it has happened. In October 2025, the University of Exeter released the Global Tipping Points Report, the most comprehensive assessment of Earth system tipping points ever compiled. Led by Timothy Lenton, Professor of Climate Change and Earth System Science at Exeter and one of the most cited researchers in the field, the report is hundreds of pages long, synthesizes data from thousands of studies, and involved over 200 contributing scientists. Its most consequential finding was a single sentence. The central estimate of the tipping point for warm water coral reefs is 1.2 degrees Celsius of global warming, and this threshold has been crossed. The current global mean surface temperature, as of 2025, is 1.44 degrees Celsius above the 1850 to 1900 pre-industrial baseline. That number comes from the World Meteorological Organization's State of the Global Climate Report, which consolidates data from 8 independent datasets, including NASA GISTEMPOM version 4, NOAA Global Temp version 6, the UK Met Office's HAD-CRUT 5, the European Centre's ERA 5, reanalysis, and Berkeley Earth. The uncertainty is plus or minus 0.13 degrees. Even at the lowest end of the uncertainty range, the number exceeds the threshold. The math does not need interpretation. The threshold is 1.2. The current temperature is 1.44. The threshold has been crossed. Warm water coral reefs, which support approximately 25% of all marine species and provide food and livelihood for roughly 500 million people, have entered the territory past the point of no return. A corroborating study published in PLOS Climate in 2022 by Adele Dixon and co-authors at the University of Leeds used 1 kilometer resolution downscaling to calculate the loss of thermal refugia, the cooler pockets where coral can survive heat stress. At current temperatures, 84% of global coral reef pixels still qualify as refugia. At 1.5 degrees, that drops to 0.2%. At 2 degrees, it drops to 0. Dixon's conclusion, stated in the paper, was that there is no safe warming limit for coral reefs. The Dartington Declaration, accompanying the Exeter Report and signed by over 640 PhD-holding scientists, states directly that already at 1.4 degrees of global warming, warm water coral reefs are crossing their thermal tipping point and experiencing unprecedented dieback. That is not a projection. That is a statement about what is currently happening. 2 systems now. The West Antarctic ice sheet, coral reefs, both confirmed crossed, both documented in peer-reviewed literature, with specific numbers, specific names, specific institutions, both irreversible, and the temporal gap between the crossing and the full consequences is measured in decades to centuries, which is why you have not felt the weight of this yet. And then there is the Amazon. In March 2022, Chris Bolton, Timothy Lenton, and Nicholas Boas published a paper in Nature Climate Change, Volume 12, page 271. The title was Pronounced Loss of Amazon Rainforest Resilience Since the Early 2000s. What they did was take the exact instrument that Scheffer described in 2009 and Carpenter validated at Peter Lake, the statistical early warning signal of critical slowing down, and apply it to the entire Amazon basin. They used vegetation optical depth data from passive microwave satellites spanning 1991 to 2016, 25 years of data covering the entire forest, and what they found was that more than 76% of the Amazon has been losing resilience since the early 2000s. The lag-1 autocorrelation, the specific statistical measure of how slowly the system recovers from perturbation, has been increasing across 3/4 of the largest tropical forest on Earth. The variance has been rising. The mathematical signature of a system approaching a critical transition is present, unmistakable, covering an area roughly the size of the continental United States. Nicholas Boas, co-author and researcher at the Potsdam Institute for Climate Impact Research, said this about the finding, and I want you to hear it precisely. He said, "If too much resilience is lost, dieback may become inevitable. But that will not become obvious until the major event that tips the system over." Read that sentence again. What Boas is saying is that the Amazon may already be committed to collapse. The early warning signal says it is approaching a tipping point. 76% of the forest is losing resilience. But the actual dieback, the part you can see from a satellite, the part that makes CNN, has not happened yet. The threshold may have been crossed. The signal says it has been crossed, or is very close. But the visible consequence, the dying forest, the smoke, the headlines, that is in the pipeline, committed but not yet delivered. The letter has been mailed, it has not arrived. And here is where the individual findings stop being individual and start becoming a pattern. Because the question you should be asking right now is whether these are isolated systems failing independently, each for its own reasons, or whether there is a connection. Whether the failure of one increases the probability of failure in the next, whether the systems are linked, whether there is, somewhere in the mathematics, a master threshold that governs not just individual tipping points, but the cascade. That question was answered in August 2018. And the answer is the worst part of everything I have told you so far. Will Stephen was an American-born chemist who spent most of his career at the Australian National University in Canberra. By the 2010 era, he had become one of the most influential Earth system scientists alive, a lead author on IPCC reports, and executive director of the International Geosphere-Biosphere Program. In 2018, Stephen, along with Johan Rockström, Timothy Lenton, and 13 other co-authors, published a paper in the Proceedings of the National Academy of Sciences, Volume 115, page 8252. The title was Trajectories of the Earth System in the Anthropocene. It would come to be known as the hothouse Earth paper. The paper mapped what the authors called a cascade topology, a web of connections between individual tipping elements showing how the crossing of one can trigger the next. Greenland ice loss disrupts North Atlantic salinity. Salinity disruption weakens the Atlantic meridional overturning circulation. AMOC weakening reduces rainfall in the Amazon. Reduced rainfall accelerates Amazon dieback. Amazon dieback releases stored carbon. Released carbon accelerates permafrost thaw. Permafrost thaw releases methane and carbon dioxide. Both feed back into further warming, which pushes more tipping points over their thresholds, which triggers more feedbacks. The connections are not hypothetical, they are measured. The directionality is confirmed by observation, and the topology means that the tipping points are not independent risks to be managed separately. They are dominoes. Stephen and his co-authors calculated that there exists a planetary threshold at approximately 2 degrees Celsius above pre-industrial levels. Beyond that threshold, the paper argues intrinsic biogeophysical feedbacks become the dominant driver of further warming, meaning it ceases to matter what humans do. The Earth's own feedback loops take over. The system drives itself, and the trajectory becomes, in the paper's own language, essentially irreversible. I need to be precise here, because the science demands it. The 2-degree threshold is a hypothesis, not a measured value. Stephen acknowledged that the threshold's location is uncertain. The paper uses language like could trigger and may cross. This is not Rignot standing on 40 years of satellite data saying the ice has already crossed the line. This is a modeling exercise with acknowledged uncertainties, and treating it as though it carries the same weight as direct observation would be dishonest. I want to be clear about that, because you deserve to know the difference. But here is what is established. The connections between tipping elements are real and measured. The feedback loops are documented. The topology is published. And the subsequent studies have not weakened the conclusion. Armstrong-McKay and 25 co-authors published a major reassessment in Science in September 2022, Volume 377. They identified 16 tipping elements in the Earth system. They concluded that 5 are already in the possible range at current warming levels. And critically, they lowered the estimated threshold for West Antarctic ice sheet collapse from the previously estimated 3.5 to 5.5 degrees down to approximately 1.5 degrees, which means the waste threshold was crossed at a much lower temperature than anyone previously thought. The picture that emerges from these studies, taken together, is not a collection of separate crises. It is a cascade architecture, a system of systems where the failure of one component increases the probability of failure in the next. And the question this raises is the one that takes us out of climate science entirely and into a field that is older, darker, and applies to something much closer to home. Is there a mathematics of collapse that applies to the systems humans build, to economies, to institutions, to civilization itself? Is there a point at which a human society becomes too complex to save? The answer is yes. And the person who calculated it did so 30 years before any of the climate tipping point research I have been describing. Joseph Tainter is an anthropologist and historian at Utah State University. In 1988, he published The Collapse of Complex Societies through Cambridge University Press. The book is not long, it is not technical, and it has been quietly reshaping how historians, economists, and systems theorists think about civilizational failure for nearly 4 decades. What Tainter did was survey every known case of major societal collapse in the archaeological and historical record. Rome, the Western Zhou dynasty, the Harappan civilization, the classic Maya, the Chacoanes of New Mexico, the Hittites, and systematically evaluate the standard explanations for each. Invasion, drought, plague, decadence, corruption, resource depletion, elite overreach. He found that in every case, the standard explanation was either insufficient or inconsistent. Drought did not collapse every society that experienced drought. Invasion did not collapse every society that was invaded. The supposed causes were present in many cases where collapse did not occur, and absent in some cases where it did. They were symptoms, not causes. Tainter's alternative explanation is mathematical. Societies, he argued, are problem-solving organizations. When they encounter a problem, whether it is a military threat, a disease, a food shortage, or an administrative challenge, they respond by increasing their complexity. They create a new institution, build infrastructure, develop a technology, raise an army, add a layer of bureaucracy. And initially, the returns on this investment in complexity are enormous. The first irrigation canal transforms agriculture. The first legal code stabilizes commerce. The first standing army secures borders. Complexity works. It solves problems. It generates returns that far exceed costs. That is why every successful society becomes complex. It would be irrational not to. And I want to be very specific about what Tainter's curve looks like, because the curve is the argument. Imagine a graph. The horizontal axis is complexity, measured as the total investment a society makes in organizational, administrative, military, and technological systems. The vertical axis is benefit, measured as the return that society gets from those investments. At the left side of the graph, where complexity is low, the curve rises steeply. Every unit of investment in complexity produces a large return. This is the founding phase, the first laws, the first roads, the first markets, the first standing army. The returns are enormous because the problems being solved are the easiest ones and the solutions are the cheapest. As you move right along the graph, the curve continues to rise, but the slope decreases. Each additional unit of complexity still produces a positive return, but the return is smaller. The easy problems have been solved. The cheap solutions have been implemented. The society is now dealing with harder problems using more expensive tools. The 10,000th bureaucrat produces less marginal benefit than the first one did. The 100th law addresses a more obscure problem than the first law did. The returns are still positive, but they are diminishing. And then the curve peaks. There is a point somewhere along the horizontal axis where one additional unit of complexity produces zero additional benefit. And past that point, the curve turns downward. Each additional unit of complexity now costs more than it returns. The society is spending resources on organizational overhead that produces negative marginal value. It is maintaining institutions that consume more than they contribute. It is adding layers of management that slow rather than enable. It is building systems to monitor systems to manage systems, and the total cost of that meta-complexity exceeds its value. Tainter argued, and this is the key, that societies do not voluntarily stop at the peak. They cannot. The problems that the complexity was created to solve do not go away just because the returns on solving them have diminished. New problems keep arriving. Military threats, diseases, resource shortages, climate shifts, administrative breakdowns, and the only tool the society has is the one it has always used. Add complexity. Create an institution. Build a system. The society cannot simplify, because simplification means abandoning the capacity to solve problems, and the problems do not stop. So the society keeps adding complexity past the peak into the region of negative marginal returns, and every addition makes the deficit worse. This is what makes Tainter's framework so devastating. Collapse is not caused by stupidity or corruption or decadence, the stories we tell ourselves about Rome. Collapse is caused by intelligence, by the rational, successful application of the only strategy available. The society does the smart thing, the thing that has always worked, and the smart thing kills it, because the strategy of adding complexity, which works brilliantly in the region of increasing returns, works in exact reverse in the region of decreasing returns. The medicine becomes the poison at exactly the point where the patient most needs medicine. Rome ran this curve to its mathematical end. In the 3rd century, the empire faced simultaneous pressures from Germanic tribes on the Rhine and Danube frontiers, Sassanid Persia on the eastern frontier, plague, inflation, and internal political instability. The response was textbook Tainter. Diocletian, who became emperor in 284, reorganized the entire administrative structure. He doubled the number of provinces from about 50 to over 100. He divided the empire into 2 administrative halves. He created a complex system of co-emperors and sub-emperors called the Tetrarchy. He imposed price controls. He built new fortifications. He expanded the army from roughly 300,000 to over 400,000 soldiers. He created new layers of bureaucracy to manage the new provinces and coordinate the new military structure. Every single one of these responses was rational. Each addressed a genuine problem, and each added complexity. Each required resources. Each created new administrative overhead, and the empire's productive capacity, already strained by decades of inflation, plague, and disrupted trade, was being asked to fund all of it. The coinage tells the story in numbers. The denarius under Augustus, roughly 27 BC, was approximately 95% silver. Under Marcus Aurelius, around 180 AD, roughly 75%. Under Septimius Severus, around 200, roughly 50%. By the mid-3rd century, under Gallienus, less than 5%. The state was dissolving its own currency to pay for the complexity that was supposed to save it. The cost of the cure was exceeding the cost of the disease, and the cure was the only thing anyone knew how to prescribe. What makes this relevant to the present, and what makes it connect to the ice sheets and the coral in the Amazon, is that Tainter's model does not require moral failure or political incompetence. It only requires a society that has been successful long enough to have exhausted its easy problems. Any society that has reached a high level of complexity, that has built intricate institutional structures to manage intricate problems, is somewhere on Tainter's curve. And the question of where is empirical. It can be studied. It can, in principle, be measured. But the people inside the system, the ones living on the curve, are the ones least likely to see where they are on it. Because from inside, every addition of complexity still feels rational. Every new institution addresses a real problem. Every new regulation responds to a genuine risk. The system feels like it is being managed, even as the marginal returns on that management become negative. But the returns follow a curve, and the curve has a peak, because societies solve their easiest problems first. The first irrigation canal exploits the most fertile land with the simplest engineering. The 100th canal requires more sophisticated engineering for less fertile land at greater cost. The first tax collector generates revenue from willing payers. The 5,000th tax collector requires enforcement infrastructure to collect from reluctant payers who have already been taxed. Each additional unit of complexity costs more and returns less. The marginal benefit diminishes. The marginal cost rises, and eventually they cross. Once a complex society enters the stage of declining marginal returns on complexity, Tainter argued, collapse becomes a mathematical likelihood, requiring only time. Not a specific external shock, not a barbarian invasion, not a drought, just time. Because the system is now spending more on maintaining its complexity than the complexity returns. It is running a deficit on its core strategy, and the only responses available to it, the only tools it has, involve adding more complexity, which makes the deficit worse. Tainter examined Rome in particular detail. The Roman response to every crisis, whether military, economic, or administrative, was to increase the size and complexity of the state. More legions, more bureaucrats, more tax collectors, more infrastructure, more subdivisions of provinces, more layers of command. And for centuries this worked. Each addition of complexity solved the immediate problem, but the cumulative cost kept rising. The debasement of Roman coinage, which Tainter documented in forensic detail, is a direct trace of this dynamic. The silver content of the denarius declined from roughly 92% under Nero to approximately 5% by the late 3rd century. The state was literally dissolving its own currency to pay for the complexity it could no longer afford. And the collapse, when it came, was not caused by the Visigoths. It was not caused by moral decay. It was not caused by lead pipes. Those are the stories cultures tell themselves after the fact. The collapse was caused by the fact that the marginal return on Roman complexity had been negative for generations, and the system could no longer sustain itself. The Visigoths were not the cause. They were the last grain of sand on a pile that had been at criticality for a century. And I want to be very specific about what Tainter's curve looks like, because the curve is the argument. Imagine a graph. The horizontal axis is complexity, measured as the total investment a society makes in organizational, administrative, military, and technological systems. The vertical axis is benefit, measured as the return that society gets from those investments. At the left side of the graph, where complexity is low, the curve rises steeply. Every unit of investment in complexity produces a large return. This is the founding phase, the first laws, the first roads, the first markets, the first standing army. The returns are enormous because the problems being solved are the easiest ones, and the solutions are the cheapest. As you move right along the graph, the curve continues to rise, but the slope decreases. Each additional unit of complexity still produces a positive return, but the return is smaller. The easy problems have been solved. The cheap solutions have been implemented. The society is now dealing with harder problems, using more expensive tools. The 10,000th bureaucrat produces less marginal benefit than the first one did. The 100th law addresses a more obscure problem than the first law did. The returns are still positive, but they are diminishing. And then the curve peaks. There is a point, somewhere along the horizontal axis, where one additional unit of complexity produces zero additional benefit. And past that point, the curve turns downward. Each additional unit of complexity now costs more than it returns. The society is spending resources on organizational overhead that produces negative marginal value. It is maintaining institutions that consume more than they contribute. It is adding layers of management that slow rather than enable. It is building systems to monitor systems, to manage systems, and the total cost of that meta-complexity exceeds its value. Tainter argued, and this is the key, that societies do not voluntarily stop at the peak. They cannot. The problems that the complexity was created to solve do not go away just because the returns on solving them have diminished. New problems keep arriving. Military threats, diseases, resource shortages, climate shifts, administrative breakdowns, and the only tool the society has is the one it has always used. Add complexity. Create an institution. Build a system. The society cannot simplify, because simplification means abandoning the capacity to solve problems, and the problems do not stop. So the society keeps adding complexity past the peak, into the region of negative marginal returns, and every addition makes the deficit worse. This is what makes Tainter's framework so devastating. Collapse is not caused by stupidity or corruption or decadence. The stories we tell ourselves about Rome, collapse is caused by intelligence, by the rational, successful application of the only strategy available. The society does the smart thing, the thing that has always worked, and the smart thing kills it. Because the strategy of adding complexity, which works brilliantly in the region of increasing returns, works in exact reverse in the region of decreasing returns. The medicine becomes the poison at exactly the point where the patient most needs medicine. Rome ran this curve to its mathematical end. In the 3rd century, the empire faced simultaneous pressures from Germanic tribes on the Rhine and Danube frontiers, Sassanid Persia on the eastern frontier, plague, inflation, and internal political instability. The response was textbook Tainter. Diocletian, who became emperor in 284, reorganized the entire administrative structure. He doubled the number of provinces from about 50 to over 100. He divided the empire into 2 administrative halves. He created a complex system of co-emperors and sub-emperors called a tetrarchy. He imposed price controls. He built new fortifications. He expanded the army from roughly 300,000 to over 400,000 soldiers. He created new layers of bureaucracy to manage the new provinces and coordinate the new military structure. Every single one of these responses was rational. Each addressed a genuine problem, and each added complexity. Each required resources. Each created new administrative overhead, and the empire's productive capacity, already strained by decades of inflation, plague, and disrupted trade, was being asked to fund all of it. The coinage tells the story in numbers. The denarius under Augustus, roughly 27 BC, was approximately 95% silver. Under Marcus Aurelius, around 180 AD, roughly 75%. Under Septimius Severus, around 200, roughly 50%. By the mid-3rd century, under Gallienus, less than 5%. The state was dissolving its own currency to pay for the complexity that was supposed to save it. The cost of the cure was exceeding the cost of the disease, and the cure was the only thing anyone knew how to prescribe. What makes this relevant to the present, and what makes it connect to the ice sheets and the coral and the Amazon, is that Tainter's model does not require moral failure or political incompetence. It only requires a society that has been successful long enough to have exhausted its easy problems. Any society that has reached a high level of complexity, that has built intricate institutional structures to manage intricate problems, is somewhere on Tainter's curve. And the question of where is empirical. It can be studied. It can, in principle, be measured. But the people inside the system, the ones living on the curve, are the ones least likely to see where they are on it. Because from inside, every addition of complexity still feels rational. Every new institution addresses a real problem. Every new regulation responds to a genuine risk. The system feels like it is being managed, even as the marginal returns on that management become negative. In 2018, Ugo Bardi, Sara Falsini, and Ilaria Parisi at the University of Florence published a biophysical formalization of Tainter's model on ArcSieve. Paper number 18, 10.07056. They translated the historical argument into a system of differential equations, treating production and bureaucracy as interacting variables in a dynamical model. Their results confirmed Tainter's central claim. The system follows a non-linear trajectory. Complexity rises, production rises with it. The two peak together, and then collapse arrives sharply. The drop on the far side of the curve is not gradual. It is steep. The system does not gently wind down. It comes apart. And the 2024 follow-up study published through the Stockholm Resilience Center took it further. They modeled societal complexity as an evolving network of laborers and administrators, and showed, in the language of the paper, that collapse becomes increasingly likely as the complexity of the model society continuously increases in response to external stresses. The model is not specific to any single civilization. It describes a class of systems, any system that responds to problems by adding complexity. Now, I need to introduce Charles Perrow, because Perrow closes the circle. Perrow was a sociologist at Yale University. He died in 2019 at the age of 86, having spent the last 4 decades of his life trying to get engineers, managers, and policymakers to understand something they fundamentally did not want to understand. In 1984, he published Normal Accidents, Living with High-Risk Technologies. The book was inspired by the 3 Mile Island nuclear incident of 1979, but its argument reaches far beyond any single technology. Perrow identified 2 properties that make a system prone to catastrophic failure. The first is interactive complexity, meaning the components interact in ways that are not fully visible or predictable to the operators. In an interactively complex system, failures propagate through pathways that were not anticipated in the system's design. Things go wrong in unexpected combinations. The second property is tight coupling, meaning the processes in the system are time-dependent and cannot be easily delayed, buffered, or rerouted. In a tightly coupled system, there is no slack. When something fails, the failure cascades immediately into the next process, without giving anyone time to intervene. When a system has both properties, when it is both interactively complex and tightly coupled, Perrow argued that catastrophic failure is not an anomaly. It is an inherent feature of the system class. He called these normal accidents. Not normal, meaning acceptable. Normal, meaning expected. Statistically inevitable. Built into the architecture, and here is the finding that connects Perrow to Tainter and Bak. When engineers and regulators try to make interactively complex, tightly coupled systems safer, the safety measures themselves add complexity. More backup systems, more monitoring equipment, more redundancy layers, more regulatory oversight, more emergency procedures, more training requirements. Each addition is individually rational. Each one addresses a specific identified risk, and each one adds new interaction pathways, new potential failure modes, new places where unexpected combinations of failures can propagate. The attempt to save a system that is too complex makes it more complex, which creates new ways for it to fail that did not previously exist. This is not a paradox. It is a mathematical property. Perrow documented it in nuclear power plants, petrochemical facilities, air traffic control systems, marine transport, and space missions. He showed that the systems designed to prevent catastrophe can be the mechanisms that cause catastrophe, not through malice or incompetence, but through the structural properties of complexity itself. Hold Perot next to Tainter. Tainter says that societies respond to every problem by adding complexity, and the returns on that complexity diminish until collapse becomes a mathematical likelihood. Perot says that in interactively complex, tightly coupled systems, every attempt to prevent failure adds complexity that creates new failure modes. The fix is the problem. The solution is the disease. The safety net is the trap. And hold both of them next to Bak. Bak says complex systems naturally organize themselves into critical states where collapse events of any size are statistically inevitable. The system does not need an external trigger. It generates its own catastrophe by growing. 3 scientists, 3 fields, physics, anthropology, sociology, 3 independently derived conclusions. And they all say the same thing. Complex systems have a built-in mathematical tendency toward catastrophic failure. The failure is not caused by something going wrong. It is caused by the system doing exactly what it was designed to do: growing, complexifying, accumulating layers of interaction and control and dependency. And past a certain point, the growth itself is the failure. The complexity is the vulnerability. And no amount of further complexity can fix it, because further complexity is the problem. This convergence is the real finding of this script, not any individual tipping point, not ice sheets or coral or the Amazon, as alarming as those are individually. The real finding is that the mathematics of collapse is universal. The same equations describe sand piles and ice sheets and forests and ocean currents and economies and civilizations. The same warning signals appear, the same irreversibility applies, and the same temporal gap between the crossing of the threshold and the visible arrival of the consequences operates in every domain. Yanir Bar-Yam, the physicist who founded the New England Complex Systems Institute at MIT, has been making this argument for over 2 decades. He stated, in a Nessie commentary on civilizational complexity, losing pieces indiscriminately from a highly complex system is very dangerous. One of the most profound results of complex systems research is that when systems are highly complex, individuals matter. Complexity leads to higher vulnerability in some ways. This is not widely understood. That last sentence should alarm you. This is not widely understood. The single most important finding in complexity science, that complexity itself is a vulnerability, is described by one of its leading practitioners as not widely understood. The research is published. It is available. It is not classified or hidden. And yet the people making decisions about how to respond to cascading system failures, the policymakers, the institutions, the governments, are operating as though more complexity is always the answer. More monitoring, more regulation, more international agreements, more technology, more infrastructure, more layers of management. Every single response adds complexity. And if Tainter is right, the civilization implementing those responses may already be past the peak of the marginal return curve, adding complexity that costs more than it returns, generating bureaucratic and institutional overhead that produces diminishing benefits while consuming increasing resources, doing exactly what every collapsed civilization before it has done, doubling down on the only strategy it has ever known, because complexity is the only tool in the box. And if Perot is right, every one of those additions is creating new failure modes that nobody is tracking, new interaction pathways, new places where unexpected cascades can propagate, new vulnerabilities in the safety systems that were supposed to prevent vulnerability. And if Bak is right, the whole thing, the entire accumulated structure of interconnected global systems, Earth systems and human systems, and the coupling between them, is a sandpile at criticality, growing grain by grain, avalanche by avalanche, with no typical failure size, and no way to predict which grain will trigger which cascade. I want to come back to Barnowski now, because his paper brings all of this together at the planetary scale. In June 2012, Anthony Barnowski at UC Berkeley and 21 co-authors published Approaching a State Shift in Earth's Biosphere in Nature, Volume 486, page 52. The paper argued that the mathematics of critical transitions, the same theory Scheffer developed for lakes and Carpenter, validated at Peter Lake, applies to the global biosphere as a whole. The biosphere is a complex system. It can undergo regime shifts, and Barnowski estimated that the threshold for a planetary scale state shift lies between 50 and 90% of the terrestrial land surface being directly transformed by human activity. As of 2012, that number was 43% and rising. The range between 50 and 90% is wide. Barnowski acknowledged that. The threshold could be near the low end, in which case we are close, or it could be near the high end, in which case we have more room. The uncertainty is real, but the mathematics of what happens when the threshold is crossed, whenever it is crossed, is not uncertain. A state shift. The biosphere reorganizes into a new configuration. And based on every analog we have, from small lakes to continental forests, the new configuration is unlikely to resemble the one that supported the development of human civilization over the past 10,000 years. And the early warning signals that Scheffer described, they are present at the global level. A companion study by Bolton, Lenton, and Bors, published in Nature Climate Change in 2022, found empirical evidence for recent global shifts in vegetation resilience. Not just the Amazon, global. The mathematical signature of systems approaching critical transitions is appearing in terrestrial ecosystems worldwide. The instrument is flashing, and it is flashing at every scale. I said earlier that I would be honest about what the science does and does not say, and I want to keep that promise. The science does not say that human extinction is imminent. The timescales are wildly different across systems. The YAS will take centuries. AMOC collapse, if the Ditlevson estimate is correct, is decades away. The Amazon could maintain its appearance for years even after resilience is fatally compromised. The Barnowski threshold has not yet been crossed. Several findings are genuinely contested by serious scientists. The Boetiger and Hastings critique of early warning signals from 2012, the prosecutor's fallacy paper, is real. False positives are possible. The uncertainty bars on many estimates are wide. I take all of this seriously, and so should you. I want to go deeper into what the Ditlevson finding means in practice, because the AMOC is the one system in this story where the consequences are not centuries away, they are decades, and they would be felt by people who are alive right now. The Atlantic meridional overturning circulation is, in simplified terms, a massive conveyor belt of water that moves heat from the tropics to the North Atlantic. Warm surface water flows northward from the equator, carrying heat energy from the tropics toward Europe and the Arctic. As it reaches the high latitudes, it cools, becomes denser, and sinks to the ocean floor. It then flows southward along the bottom of the Atlantic, eventually rising again in the southern hemisphere, warming and beginning the cycle again. This circulation is responsible for an enormous amount of heat redistribution across the planet. Without it, Europe would be dramatically colder. The Scandinavian countries, the British Isles, and much of Northern Europe are habitable largely because the AMOC delivers heat from lower latitudes. London sits at the same latitude as Calgary, Alberta. The reason London does not have Calgary's winters is the AMOC. The concern about AMOC collapse goes back decades, but for most of that time, it was treated as a theoretical possibility, something that might happen in centuries under extreme warming scenarios. The IPCC's assessment reports have consistently rated AMOC collapse as low probability. The most recent full assessment, the sixth assessment report from 2021, concluded that AMOC is very likely to weaken during the 21st century, but that collapse before 2100 is considered unlikely, with medium confidence. That was the institutional consensus. Peter Ditlevsen and Suzanne Ditlevsen at the Niels Bohr Institute in Copenhagen challenged that consensus directly. Their paper, published in Nature Communications on July 25, 2023, used a statistical approach that was fundamentally different from the modeling approach used by most AMOC researchers. Instead of running climate models and asking when AMOC collapses in the simulations, the Ditlevsens used observational data. Specifically, they used a proxy for AMOC, strength based on sea surface temperature patterns in the North Atlantic, a proxy developed by Nicholas Boas, the same Boas from the Amazon Resilience paper, and applied statistical techniques from the field of extreme value theory to estimate the most likely timing of a critical transition. The result was jarring. Their central estimate for AMOC collapse was the year 2057. The 95% confidence interval ran from 2025 to 2095. The central estimate was 3 decades away, within the lifetime of most people watching this video. And the consequences of AMOC collapse, modeled in numerous studies, include temperature drops of up to 15 degrees Celsius in parts of Northern Europe within decades, catastrophic disruption of monsoon systems in West Africa and South Asia that billions of people depend on for food production, collapse of marine food chains in the North Atlantic, and a dramatic reorganization of global weather patterns. I need to repeat the caveat I gave earlier because it matters. This finding is contested. Chen and Tum argued in a 2023 paper that the proxy Bohr's developed contains artificial variance from changes in observational coverage. Ben Yami and colleagues argued that the statistical uncertainties are too large to support a prediction this specific. The IPCC has not revised its assessment, and a 2025 paper in Nature Climate Change directly addressed the ambiguity of early warning signals for climate tipping points, cautioning that the statistical tools used may produce false positives. The Ditlevsen paper published an author correction in 2025 addressing code errors, but did not retract its central finding. So the honest framing is this: there is a credible, peer-reviewed study placing AMOC collapse within decades. There are credible peer-reviewed critiques arguing the estimate is premature. The question is not settled, but the question being asked, whether the circulation system that keeps Europe habitable might shut down within the lifetimes of people living in Europe right now, is a question that until very recently, nobody thought we would need to ask this soon. The fact that it is being asked, that the data has reached a point where a serious estimate with a central year of 2057 can be published in Nature Communications and survive peer review, is itself a signal, not of certainty, of proximity. The conversation has shifted from could this happen in centuries to could this happen in decades? And that shift happened because someone pointed Scheffer's instrument at the AMOC and the instrument flickered. I want to pause here and talk about something that connects all 5 of these crossings, because there is a feature they share that is easy to miss if you are looking at them individually. The feature is the temporal gap. And the temporal gap is, I think, the single most dangerous property of complex systems. Here is what I mean. When Rignaud said the YS had passed the point of no return, the ice was still there. It is still there right now. It will be there for centuries. The collapse is committed, but not visible. When the Exeter report said coral reefs have crossed their thermal tipping point, coral reefs still exist. You can go snorkeling on them today. They are degraded, they are bleaching more frequently, they are losing species, but they are still there. The tipping point was crossed. The collapse has begun, but the process that transforms crossed threshold into no more reefs takes decades. When Bolton and Lenton and Boers said the Amazon is losing resilience across 76% of its area, the Amazon is still green. Satellite images show forest. The canopy is still there. The resilience loss is invisible from above. It exists only in the statistical properties of the vegetation data. The dieback, if it comes, will come later. Maybe years, maybe decades. In every case, there is a gap between the moment the system becomes unsavable and the moment the consequences become visible. And in every case, the gap creates an illusion of stability. The system appears to be functioning because the outputs look the same. The ice is still ice. The forest is still green. The reefs are still there. The AMOC is still circulating. The only thing that has changed is the internal dynamics, the resilience, the recovery rate, the distance from equilibrium, the things you can only see with the instrument. This is the gap where denial lives, not deliberate denial, not conspiratorial denial. The denial that is built into the human perceptual system. We assess the state of the world by looking at it. We look at the ice and it is there. We look at the forest and it is green. We conclude that things are fine. And things look fine. The lake still looks like a lake. Peter Lake looked like a perfectly normal lake for over a year after the warning signals appeared in the data. If you had visited it, if you had put your hand in the water, if you had watched the fish swim, you would have concluded it was fine. You would have been wrong, but you would have needed Carpenter's instruments, his training, his statistical framework, and his 3 years of daily data to know you were wrong. Without those, the lake was indistinguishable from a healthy lake. Now scale that up. Scale it to a planet. Scale it to ice sheets the size of France and forests the size of the continental United States and ocean circulation patterns that span the entire Atlantic. Scale it to a species of 7 billion individuals who assess the health of their world by looking at it, and whose institutions assess the health of their world by reading reports compiled by committees who summarize findings from papers written by scientists who have the instruments. By the time the finding in the paper reaches the committee report, reaches the policy document, reaches the decision maker, the temporal gap has been compounded by an institutional gap. The crossing happened. The paper was published. The report was compiled. The committee met. The policy was drafted. The negotiation began. And through all of that, years have passed, and the system has moved further past the threshold, and the gap between the crossing and the consequences has been filled not with action, but with process. More complexity, more layers, more institutions, more reports. Tainter would recognize the pattern. Perot would recognize the failure mode. Bak would recognize the criticality. The system responds to the signal of its own collapse by adding complexity to the process of interpreting the signal, and each addition of complexity costs more and returns less. And the ice does not care about your committee. The ice does not care about your report. The ice has its own math, and its math does not wait for institutional processes to conclude. I want to address one more thing before I bring this to a close. because I know the objection that is forming in some viewers' minds, and it is a fair one. The objection is this: the systems I have described, ice sheets, coral, forests, ocean currents, are natural systems. They obey physics. They have thresholds that can be measured. But human civilization is not a natural system. It adapts. It innovates. It creates new technologies. It discovers new energy sources. It restructures its institutions. The capacity for conscious self-modification, the capacity to see the problem and change course, is the thing that separates human societies from sand piles and ice sheets. And therefore, the argument goes, the mathematical parallels I have drawn are false. Human civilization is not a sand pile. It is something else, something that can read the data, understand the curve, and choose a different path. I take this objection seriously. I think it has real force. The history of human civilization is, among other things, a history of escaping traps that should have been fatal. The Malthusian trap, the energy trap, the information bottleneck. In each case, a technological or organizational innovation created capacity that the previous system could not generate. The Green Revolution, the Industrial Revolution, the Digital Revolution. Each one broke through a ceiling that the existing complexity could not breach and opened a new phase of growth with high returns on new complexity. The question is whether another such breakthrough is possible. And the honest answer is that nobody knows. But I want to be precise about what the mathematics says and what it does not. The mathematics does not say that breakthrough is impossible. It says that the window for breakthrough narrows as the system moves further into the region of declining marginal returns. It says that the cost of implementing any breakthrough increases as institutional complexity increases, because every new technology has to be integrated into a system that is already straining under the weight of its existing complexity. It says that the feedback loops between Earth system tipping points and civilizational tipping points are bidirectional. The Earth system failures stress civilization. The civilizational response adds complexity. The complexity adds costs. The costs reduce the resources available for breakthrough. And the Earth system failures continue regardless. Tainter addressed this objection directly in his later work. He pointed out that the Roman Empire also innovated. It built roads and aqueducts and legal systems and military technologies that were genuinely brilliant. Innovation does not exempt a society from the mathematics of diminishing returns. Innovation is subject to the same curve. The first innovations in any domain produce the largest returns. Subsequent innovations in that domain are incrementally smaller. The cost of research and development per unit of useful output rises over time. The number of scientists needed to produce a given rate of discovery increases. The complexity of the research infrastructure itself grows. The returns on investment in innovation follow Tainter's curve, just like the returns on investment in bureaucracy. I am not saying that collapse is inevitable. I am saying that the math describes the trajectory we are currently on, and the trajectory points in a specific direction, and multiple independent measurements confirm that several subsystems have already crossed their respective thresholds. And the institutional system tasked with responding is exhibiting precisely the behavior that Tainter's model predicts from a system in the declining returns phase of the complexity curve. Whether the trajectory can be changed is a different question from whether the trajectory exists. And the trajectory exists. It is measured, it is published, it is in the data. But here is what I cannot get around, no matter how much I try to be measured about it. The mathematical framework is consistent across every field that has tested it. The same equations describe sandpiles and ice sheets, and forests and civilizations. The instrument works. It has been validated. The warnings are flashing. Multiple systems have confirmed crossings. The connections between those systems are mapped, and the cascade topology is documented. And the institutional response of the global civilizational system has been to add complexity, which is exactly what Tainter's model predicts a civilization in the diminishing returns phase will do, and exactly what Perrow's framework predicts will create new failure modes. There is a concept in complexity science called hysteresis. It refers to the phenomenon where a system that has been pushed past a threshold cannot be returned to its original state simply by reversing the push. You heat water to boiling and it turns to steam. You cool the steam and it condenses back to water. The path up and the path down are the same. That is a system without hysteresis. Now consider a lake that has been eutrophied. You load it with phosphorus and it flips from clear water to green algae. You remove the phosphorus and the lake stays green. You remove more phosphorus, still green. You have to reduce phosphorus to a level far below the concentration that originally triggered the flip before the lake will recover. The path down is not the reverse of the path up. The system has hysteresis. Breaking is easier than fixing. By orders of magnitude. Every single system I have described in this script has hysteresis. You can reduce carbon emissions to zero, and the West Antarctic ice sheet will not re-advance. The grounding line is gone. The bedrock slopes the wrong way. The positive feedback loop is running. You can cool the ocean below 1.2 degrees, and the coral reefs will not spontaneously recover. The thermal damage to the symbiotic algae that corals depend on is not reversed by subsequent cooling. You can stop deforesting the Amazon, and the resilience loss will not automatically reverse. The feedback between drought stress, fire vulnerability, and reduced transpiration is self-reinforcing. The hysteresis is the horror, because it means that even if every optimistic scenario plays out, even if renewable energy deployment exceeds all projections, even if carbon capture technology works at scale, even if every nation on Earth meets its climate commitments, the crossings that have already occurred are permanent. The WAIS commitment is locked in. The coral reef threshold is behind us. Those are facts about the past. They are not arguments about the future. You can argue about whether we will cross the next threshold. You cannot argue about whether we already crossed the last one. The data is in. The papers are published. The crossings are confirmed. And here is where the personal implication arrives. The part where the mathematics stops being about ice sheets and forests and starts being about you. You live inside a complex system. You are a component of it. The food you eat was produced by it. The water you drink was treated by it. The electricity powering whatever device you are using to watch this was generated and distributed by it. The economy you participate in, the institutions you interact with, the infrastructure you depend on, all of it is the product of a civilization that has been adding complexity for 10,000 years. And that civilization, like every complex system that has ever existed, sits somewhere on Tainter's curve. I do not know where. Nobody does. That is one of the properties of being inside the system. From inside, each addition of complexity looks rational, necessary, and manageable. From inside, the peak of the curve is invisible, because the peak is defined by the relationship between cost and benefit, and the costs are distributed in ways that are hard to measure, and the benefits are defined by the institutions that are themselves the source of the cost. The Roman bureaucrats who created the new provinces under Diocletian believed they were solving a problem. They were. They were also accelerating the collapse. Both things were true simultaneously, and neither was visible from inside the system that was doing it. What I can tell you is what the math says about the general properties of the situation. Bak says complex systems evolve toward criticality. Tainter says the returns on complexity diminish. Per says fixes add complexity that creates new failure modes. Scheffer says there is a measurable signal as the threshold approaches. Carpenter proved the signal is real. Rignot documented the crossing. The Exeter report documented more crossings. And Barnowski suggested the planetary biosphere itself is approaching a state shift. Each of these findings is individually alarming. Taken together, they describe a single coherent phenomenon viewed through different disciplinary lenses. And the phenomenon is this. Complex systems grow. They accumulate structure. They solve problems by adding layers. And at some point, the layers become the problem. The complexity that was supposed to protect the system becomes the weight that breaks it. The point at which this happens is calculable. In some systems, it has been calculated, and in some of those systems, the calculation shows that the point has already been passed. The question of whether that applies to the system you are sitting inside of right now is not one I can answer with the same certainty that Rignor brought to the ice. The data for civilization is messier. The variables are more numerous. The system is harder to monitor, and the people doing the monitoring are components of the system being monitored, which introduces a circularity that does not exist in glaciology. But the math is the same. The equations that describe the sandpile, describe the ice sheet, describe the forest, describe the civilization. The universality is the finding, and the universality is what makes the past tense crossings in the Earth system so much more disturbing than they would be if they were isolated events. Because they are not isolated. They are examples. They are what the math looks like when it is applied to systems we can measure from outside. And the question is whether the system we cannot measure from outside, because we are inside it, is following the same curve. I spent an unreasonable number of hours reading the primary literature on this, going back to Bak's original 1987 paper and forward through Scheffer 2009, Carpenter 2011, Barnowski 2012, Rignot 2014, Stephen 2018, Armstrong McKay 2020, Bolton 2022, Ditlevsen 2023, the Exeter Report 2025. Hundreds of papers, thousands of citations, a field that has been building quietly across multiple disciplines for nearly 4 decades. And the thing I still do not fully know how to process is this. The mathematics is not disputed. The power laws are real. The critical slowing down is real. The diminishing returns on complexity are documented across every historical case of collapse. The tipping points are crossed. The cascades are connected. The instrument works, and nobody convened the meeting. Nobody put Bak and Tainter and Per and Scheffer in the same room and said, "You are all describing the same thing. Your equations are compatible. Your findings reinforce each other. Your separate fields have independently converged on a single conclusion. And that conclusion is that the system we are all part of has mathematical properties that make catastrophic failure not an aberration, but a certainty. The only question is timing. And for several subsystems, the timing is in the past. That meeting has never happened. The disciplines remain separate. The ecologists publish in ecology journals. The physicists publish in physics journals. The anthropologists publish in anthropology journals. The sociologists publish in sociology journals. And the synthesis that should terrify everyone, the finding that all 4 fields agree on the mathematics of inevitable collapse, exists only as an implication. that you have to assemble yourself by reading across boundaries that the institutional structure of science does not encourage you to cross. I think about Per Bak, dying at 53 in Copenhagen, frustrated that his colleagues would not see the connections he saw. I think about Tainter, writing in 1988 that once a complex society enters the stage of declining marginal returns, collapse becomes a mathematical likelihood, requiring only time. I think about Perrow, spending 4 decades trying to explain that the fixes are the failures. I think about Scheffer, building an instrument that detects dying systems, and Carpenter, proving it works, and then both of them watching as the instrument was pointed at the world, and the readings came back, and the papers were published, and the findings entered the literature, and the literature was cited, and nothing changed. The sandpile is still growing, a grain at a time, and there is no one whose job it is to count the grains. There is only the math, and the math does not negotiate. Rignot said it. May 12, 2014. The system is in a chain reaction that is unstoppable. It has passed the point of no return. He was talking about ice, but the equation is the same. For everything that grows, everything that complexifies, everything that accumulates layers until the layers become the weight that brings it down. The threshold was crossed quietly, in the data, in the math, in the satellite readings that almost nobody sees. And the gap between the crossing and the consequences, the gap Boas described, the period where the system looks stable because the visible collapse has not yet arrived, that gap is where you are standing right now. Not before the threshold, not after the consequences. In the gap, where the math has already turned and the lake still looks like a lake and the sand is still falling.